All right, hey everybody. We're going to cover 2.6 today, the squeeze theorem and other important trig theorems. So before we begin, I want us to warm up by thinking about the question of what is the range of sine x and cosine x? In other words, what can they yield, right? What's the smallest output and what's the largest output? Simply put, both of their answers are always around the unit circle, right? So if we envision that unit circle, the y-coordinates only go from -1 until +1. Okay, so that's important. First of all, it's a symmetrical range. Okay, and it's completely bounded. There's no exception. Sometimes when we look at domains or ranges, it's all real numbers except this one, or greater than this, but open-ended on the other side. So the fact that we're capped on both sides and that range is symmetrical is really helpful for the squeeze theorem. Okay, so how can we evaluate a limit when direct substitution fails, right? So this is what we covered in the last section. We looked at things like factoring and canceling, right? And this is for those indeterminate forms. We looked at the conjugate. We looked at like rewriting trig, I'll call that. Okay. So today we're going to look at a few more things where, yeah, we know it's indeterminate, but none of these three techniques are going to help us. Okay, the first one is the squeeze theorem. I'll be completely honest, this, although it is applicable, it works, it's not something that we're going to see a ton. Okay, so squeeze theorem states that assuming that x does not equal c, okay, in some open interval containing c, that we have three functions. This first inequality is saying we have a lower function, we have the function f that we are trying to evaluate the limit for, and we have the upper function. And this inequality is saying that the outputs, the range, right, of f always stays between L and U. And if we can prove that, the function values follow that behavior, then therefore the limits, one more condition. If we can prove that, and we can prove that the limit of L as x approaches c is equal to the limit of U as x approaches c is equal to some value L, right? If these two conditions exist, 1, 2, then we can make the statement that the limit of f as x approaches c exists, and it must also be equal to L. So those are the three steps in the squeeze theorem. They're always going to look really, really similar, and they're pretty much always going to yield the same answer. Graphically speaking, right, what we're envisioning here with our inequality, the first, step 1. So we have green, we have that upper function where the outputs, the y's, are the largest. We have blue, that lower function where the outputs are the smallest, and we have pink falling in the middle. But what's important to note is that at C, right, they converge. They all come to the same output, right? Their function values are actually the same. And therefore, the limits are going to be the same at that moment. Okay, so our first example. So I've got the graph shown here. We won't always see the graph. But the example that we're looking at, and they tend to resemble each other, right? They tend to look pretty similar because there's not too many functions that we can use this concept for. So show that the limit as x approaches 0 of x times sine 1 over x is 0. We're trying to prove this. Now, many of us will want to just say, well, let's just plug it in, right? Because if x takes on the value of 0, we have 0 multiplied by something. Well, then done. It's 0. But we have to slow down because, yes, that would be true if sine of 1 over 0 was defined, and it's not. So because part of it is undefined, we really have that 0 times maybe an infinite behavior. We're not too sure. So this is an indeterminate form. Okay. We need to remember the premise of this working, right? The fact that sine x stays between 1 and -1. Okay? That is that range that we talked about in the warm-up that allows these to be proven using the squeeze theorem. Okay? So because sine of something, right, when I just write it as the generic sine x, sine of something stays there, well, I can rewrite it that sine of 1 over x also stays between 1 and negative 1 for that matter, right? Sine of anything. Okay, so from there, we can look at ourselves and say, well, I need to make this inequality, at least the middle of it, right? The middle part is my f, needs to match what's up top. Okay, we're looking to evaluate this limit at 0. Okay, so we're not going to multiply by just a regular x to make the middle match, make the function the same. We're going to multiply the inequality by absolute value of x. The reason that we are doing this, first of all, at 0, the place that we're evaluating the limit at, the absolute value does not change my f function, my inside function. So I'm multiplying the outsides as well, right? And in an inequality, I have to maintain equality, so the outsides and the middle are being multiplied by absolute value of x. I'm choosing absolute value of x because that is a function that we know that has sort of that mirror image, right? We need a lower function that's always below. We need an upper function that's always above, that middle pink function in our graph here. If I only multiplied by a normal x, then on the left side of my inequality, I would have negative x. Well, that's a line with a negative slope, so that would end up cutting through my pink function. So if I did that, I'm going to color over our graph right now. I would just have, right, a negative sloped line. Then therefore, stipulation number 1 would not hold true. I don't have an upper function and a lower function that's always above and always below. I would have a crisscross happening at 0. So my theorem fails. So I have to have these absolute values because they take on that mirror reflective image that we need where where the negative x, where the positive absolute value of x matches that green, that upper. The negative absolute value of x matches that blue, the lower. And the inside is the pink. I don't have pink on my color tool right now, so I'll just use red. Okay, so we have satisfied number 1 of the squeeze theorem. Okay, so we have our upper and our lowers, and now we can say since the limit as x approaches 0 of negative absolute value of x is equal to 0 through direct substitution, through graph interpretation, through anything, and the limit as x approaches 0 of the positive absolute value of x also equals 0. The squeeze theorem tells us that the limit, and now we can state that the initial problem, the limit is of x sine 1 over x, must also equal 0. Because we had 1, 2, and we can make the third statement. You have to show me those 3 steps. Okay, the first thing, acknowledging our range restriction, that's kind of underlying background knowledge that, yeah, we have to have. But 1, 2, 3 steps have to be shown in order to prove the squeeze theorem. Second example, like I said, they're going to look really similar. Right? We're always going to be trying to evaluate a limit at a moment of something that's indeterminate. So we're causing a 0 and a denominator in this case. We're causing a 0 multiplied by an infinite scenario is what's happening. So we are indeterminate. Right? Indeterminate could be the 0 over 0, which we studied in 2.5 a lot. Could be 0 times infinity, which is what we're seeing here. There's more than one indeterminate form. In the simplest way that I can explain indeterminate, it just means that it's not undefined, right? But I don't really know what the answer is. I might think it's this, I might think it's that. I'm not too sure, so I have to investigate further. The key is you can always investigate further. There's going to be a method that allows you to manipulate it to come up with that answer. Okay. All right, so we know that cosine takes on values between 1 and negative 1, and therefore this cosine of 1 over x minus 2 also remains between 1 and negative 1. Okay? We take a look at our middle inequality. We say to ourselves, well, I need f of x. I need exactly what's in the original problem to be in the middle. Using the absolute value concept again, I now choose to multiply each of the three parts of the inequality with absolute value x minus 2. So we have the negative Now, even though the middle doesn't perfectly resemble the original function, remember at 2, when we are evaluating this limit, it doesn't change signs, so we're okay. Right? If I plug in 2 to that absolute value inside f of x, it wouldn't impact us. All right, so now we have created our lower, our function, and our upper in an inequality that will always hold true. And therefore I can go ahead and evaluate the limits as x approaches 2 of negative absolute value x minus 2. If we plug in 2, direct substitution, we get 0. And the limit as x approaches 2 of positive x minus 2 also equals 0. And therefore, the squeeze theorem tells us that the limit as x approaches 2 of x minus 2 cosine of 1 over x minus 2 also equals 0. Okay, I'm going to leave this one as an extra. It's literally the same exact thing, so we can either do this in class if you need more practice, or you can try this one on your own. Okay, so now moving into other important theorems from trig. Okay. So think about sine x over x in 2.2, right? We saw that example, if you recall. We saw that example numerically and graphically. So here's those table of values for you again. Okay. We've already proven that this limit is equal to 1 by looking at the table of values. Sine x over x specifically, as x approaches 0, because the numbers, as we get closer and closer to 0, on the left and on the right, both equal 1. Okay? So this is now a given. We're going to use this as a pretty bold statement. Okay? We proved it through one method, so now we're going to use this to our knowledge. So theorem 2 in this section, important trig limits. These are two that you definitely want to memorize. State that the limit as theta approaches 0 of sine theta over theta equals 1. And the limit, we could prove this one using a graph or using a table as well. The limit as theta approaches 0 of 1 minus cosine theta over theta is equal to 0. Okay? So the sine theta one goes to 1, the cosine theta pattern goes to 0. Okay. We're going to investigate, right? So the theorem clearly shows a sine theta over theta or cosine theta over theta. So we're going to investigate what might happen if we change variables. What if we have a sine 4h over h as h approaches 0? What do you think might happen? Jot down before I start talking, jot down an answer that you think might come out. What do you predict? So we're going to use the table of values. If I put this into the graphing calculator and manipulate my table of values so that I can get these exact outputs, I'll put them in here so we don't have to waste any time, but that's where these are coming from. Graphing calculator, table of values. And we can see that on the left, as we get closer and closer to 0, the output gets closer and closer to 4. Now, this method, though, is more time-consuming. And, of course, problems will start to come at us that are a little bit more complicated, so we don't want to guess. Right? Many of us might have guessed 4. but we want to come up with a way that we can algebraically prove this. Okay, so we love the number 1 in math, right? We can use it in so many ways. We can manipulate it and multiply things by 1. But we have to come up with that special value depending on the problem we're looking at. So here, right, if we have a sign of 4h, 4h is essentially our theta. Right? So we need that 4h in the denominator. So we're going to take our original problem and we're going to multiply it by 4 over 4. What this does for us is it allows us to group things as we wish and isolate the part that we don't need. So that extra 4 in the numerator I don't really care about right now because I need to fully isolate my theorem. And once I clearly see my theorem from the previous page of notes, then I can state, well, sine theta over theta as h goes to 0 is equal to 1, and therefore this is equal to 4 times 1, or 4. Okay? So you have to find the theorem. You have to prove it. You have to show your work. You can't just jump to an answer. I could have shown that this limit can go here and here, or, right, so I can have limits of two things, limits of a constant and limit of that theorem, or I can just pull the coefficient out in front. Okay? I'm just bringing this page back up, reminding us that we have these basic limit laws. We saw this earlier on in the chapter. So addition can be broken apart, coefficients can be pulled back out, multiplication, etc., and powers. All of those operations can be taken out. So that's basically what we just did, right? We removed the 4. The other one also is the division, as long as that denominator does not equal 0 at C. Okay. We'll continue to manipulate all of these so that we can get at our theorem. So this one, sine squared t over t. We can't automatically jump to the fact that the answer is 0 or something like that because it's not, right? We have what seems to be, well, let's see, sine at 0 is equal to 0. So we have a 0 over 0. We have an indeterminate form, so we can't jump to an answer yet. We need to manipulate this and we need to find a theorem. Looking at this initial problem, I know that it's obviously the sine theorem. So in my work, I am searching for this. Okay. This one, for some reason, tends to be challenging for us to identify what we need to do, maybe because it is a little bit simpler. So we're going to take the fact that there's an exponent, it's a sine squared, and write it as multiplication, repeated multiplication. Right? And then that's all we need, because now we can group together a sine t over t and keep separate the other sine t. And then we can take that extra step. I won't be picky about this step. And write it as this. Okay? And now for this reason, right? This is our theorem, this is 1. Well, sine at 0 is 0, so now we have a 1 times 0, or 0. Okay, so tan 4x over 9x as x goes to 0. So immediately, when we see a tan, we're going to change it to sine or sine over cosine.
No, every night, but not every time.
And I'm going to, instead of division of 9x, I'm going to write it as 1 over 9x. Okay? So now we're seeing it. We have a sine theta over theta. We have the workings of it. So that's what we're looking for. Remember, that one equals 1 as we take the limit as theta goes to 0. Okay. So how do we turn a 4x and a 9x into the same theta, though, right? So I'm going to group these two together. and I'm going to rewrite this. Okay, so 4x and 9x, of course, are not the same. There's a couple ways. We could pull the 9 out and kind of ignore it and just multiply by a 4 because we don't have to have that 9 to begin with. We could put the 9 with the cosine. Or we can multiply by 4/9, right? Which essentially divides that 9 out in the same way. Okay, so 4/9 over 4/9. That's preference on you guys, but ultimately those thetas have to be the same. So up top, I'm going to have a 4/9 sine of 4x because remember that 4/9 can't go into the theta. We can't change the theta. And on the bottom, we're going to have those 9's cancel out. We're going to have a 4x. Okay?
He is. He's doing his little...
So theta can't change. The value underneath can change.
Yeah.
Theta inside of the sign can't change, I should say. All right, so now we've got our theorem. We have an extra 4/9. That's just a constant coefficient. Sine of 4x over 4x as limit goes to 0 is going to be 1. And 1 over cosine of 4x. If we evaluate that directly, cosine at 0 is 1, so that's equal to 1. So our answer is 4/9. Okay. So there's one more page here. I'm going to choose to leave this blank, and these are examples that we can go over in class. I will let you know that this is the squeeze, right? And then the other 3 are your other trig theorems that you're going to look to find, right? So there are some cosines in there. Okay, we can see them now. You're looking for those 1 minus cosine thetas over thetas, and those are equal to 0. Okay, so go through these on your own. We will go through them together as needed in class to make sure that we're all on the same page. Okay. So ignore this for now. We summarize some of those techniques, and now our other options are these trig theorems. But what should our first option always be? Always want to try direct substitution. Sometimes limits are as easy as that. Remember, functions are continuous most of the time. But, of course, we're really evaluating limits at those points of discontinuity, and that's what we're going to get into in the coming sections here. But always try direct substitution first. Okay? All right, talk to you next time. Bye.